We're here at Engineered Victories. I just wanted to talk about dyno, engine dynos for some of you people that don't know exactly how they work or the way that they work. Kind of dispel some of the myths that people have about dynos. This dyno is a Superflow Powermark dyno. It's fairly new, it's about a year old. A dyno measures torque. It doesn't measure horsepower. Horsepower is a calculation derived from RPMs and torque. The equation is torque times RPMs divided by 5252 equals horsepower. So the dyno only measures torque through a load cell. So this is the load cell right here that measures the torque that the absorber or the water brake is holding back. This is what holds back the engine, and it's trying to rotate in the same direction as the drive shaft that's connected to the motor. This load cell is what's holding this from rotating, and however much this is holding back is the torque of the engine. So that is how it gets its torque number, and then through calculations and the equation that I mentioned earlier is how it spits out the horsepower at you. This dyno here has a drive shaft that is connected to the engine that goes through here and connects to this water brake. Some engines don't have some dynos don't have a drive shaft, and this is connected up here, but this one has a drive shaft. This dyno also has 8 O2 sensors. They're not connected to this engine, but we can put an O2 sensor in every port so that we can make sure that on a high horsepower engine, where it's really important that every cylinder has the correct air fuel mixture, such as like a turbocharged motor. It's real easy to burn pistons and stuff like that, so you want to make sure you don't have one lean cylinder, or else you get into big problems. You have a $50,000 piston blender. You don't want that. Also, this measures the amount of air going into the engine. There's also this fuel line here, which has a flow meter built into it to measure the amount of fuel going to the engine. Through the amount of air and the amount of fuel, you can calculate the brake-specific fuel consumption. Brake-specific fuel consumption is another equation. It is the amount of fuel per horsepower per hour that the engine is using. So you can see how efficient your engine is through the brake-specific number. In order to get the proper brake-specific number, you need proper fuel, proper air, and also the weight of the fuel has to be inputted into the computer before you start. So you need the specific gravity of the fuel in order to get that. This is the sensor that gives you the conditions of the atmosphere in the room, such as the temperature, the humidity, the barometric pressure. Now, one thing that a lot of people have problems with is this guy's dyno says this and this guy's dyno says that, and his is wrong, or his is high, or his is low. That is more to do with the dyno cell itself and the conditions in the dyno cell than it is the dyno itself. It's very important to have a good dyno cell. Up here we have an adjustable vent in the roof to let air in, so that we can keep the proper atmospheric pressure in this room through a complete pull. The fan on the back side of the room keeps the fresh air coming in through the vent, and we need to change the air in this room 10 times per minute. So your fan has to be capable of changing 100% of the air in here 10 times per minute, or else you'll end up getting contamination. Anyone that's dynoed before and has some dyno experience has probably had a exhaust pipe fall off and starts putting exhaust into the room, and you'll see on your dyno that you've automatically lost 15 or 20 horsepower, and then you go, oh my god, what's happening to the engine? Is it starting to come apart? And then you realize that you've just contaminated the room, and 15 horsepower just like that. So once again, it's very important to have a good dyno cell, just as important as it is to have a good dyno. So let me take you into the other room and we'll talk about correction factors and inertia correlation and things like that. Okay, so now we're here in the control room. Dyno and engines on the other side of the safety glass. And I wanted to explain a couple things to you. A lot of times on YouTube, I've seen comments that you'll be looking at a sweep of an engine, and right here where it says engine horsepower or engine torque, it won't match what the dyno operator is claiming on YouTube. But this is just the actual horsepower and the actual torque of what the engine is producing at that time. That is uncorrected. So usually the corrected number is higher than what the uncorrected number is, and it's not that the engine builder or the dyno operator is lying to you guys. It's just that you're reading the uncorrected power and he is saying the corrected power. So here's a few things. Let me go over what you read on the dyno when you have an engine being put on there. You've got the oil pressure here. Of course, this engine isn't running, so it's not reading the running values. But this is oil pressure. This is manifold pressure, which is either going to be vacuum or in a boosted application boost. Fuel pressure, which is going to be your carbureted fuel pressure of 6.5, 7 pounds, or a fuel injected pressure, 58 pounds, 35 pounds, whatever your system needs. This is the water coming out of the dyno. What a dyno does is it takes water and turns it into heat energy. And so the water going in is heated up, and that's what's converting the horsepower or the energy of the engine into heat. So right now it's 47 degrees. We haven't had this thing running, but if we were to start this engine and make a pull, this might go up to 150 degrees. One thing that you always want to make sure of is that you don't boil the water inside the water break. So if this gets up 180 degrees, you need to add more water, make some adjustments so that you don't boil the water in there. This is the coolant out, which is the coolant temperature of the engine, your oil temperature, and your battery voltage. So for this section here, when you dyno an engine, you want to make sure that you have back-to-back runs that are comparable. So we want the oil temperature to be the same from run to run. Pretty close, within 3 or 4 degrees would be great. The water temperature is not as important, but you want that to be the same too. The other things are pretty much going to stay the same. Right here is your air-fuel ratio in the left side and the right side of the engine. This would constitute for only one bank left and one bank right, this wouldn't do all 8 that we have the capabilities of doing. This is a blow-by meter. This would show you how much blow-by you have coming through the engine. On a worn-out engine, it would show if the engine needs a rebuild as far as the rings are concerned. It also would show if a ring package or a piston skirt design or a bore finish is better or worse as you do different types of finishes. So this is our test setup here, and what this says in this particular test is that we're going to start the run at our lower RPM of 2,500 RPMs, and we're going to end it at an upper RPM of 6,000 RPMs, and our step size is 500 RPMs per second, so that is the rate of the sweep that we're doing. This is programmed into the computer before you start the run. Now down here is your atmospherics. This is what is showing to be the corrected number. So today, in this particular situation, we are 2% or 2.2% higher than what we're going to read. So what it's going to do is it's going to take this number here and it's going to multiply it by 2% or 1.02, which is going to give you the corrected number, which is why the corrected number that the dyno operator is talking about is usually higher than what this number is. This is a Society of Automotive Engineers have come up with a correction factor in order to standardize dynos in different areas, different atmospheres, different temperatures, different altitudes. So what it does is it makes it so that in theory, because it doesn't work 100%, but in theory, at any altitude, whether you're in Florida or Denver or in the desert or in 30-degree weather, you're going to have the same corrected number. So that is why we have a correction factor. It takes the barometric pressure, the humidity, and the air temperature and puts them into an equation to come out with how many percent it's going to add or subtract to give you your corrected number. So that's the difference between an observed number or an actual number and a corrected number. One more thing to consider is the rate of the sweep. When the factories like GM do a dyno test, they do it at a steady state, which means they'll run it up to 5,000 RPMs and hold it there and measure the power. If the faster you sweep it, the lower the horsepower number is going to be. The slower you sweep it, the higher it's going to be. So therefore, it only goes without saying that a steady state is the actual horsepower that the engine makes, because it's not sweeping at any rate, it's staying in a steady state. So in this particular dyno, they have what is called inertia correlation, which takes into consideration the weight of the drive shaft and the rotor in the water brake, and it takes that and loads that into a correction factor. Okay, so this is our graph screen. This is our torque graph in blue here, and this is our horsepower graph here. Notice where they cross. They cross here and at the RPM of 5252, 5,252 RPMs is where they always cross, because that's the equation, as I talked about earlier. So these numbers here, the 415 and 447 for torque, that's what this engine had observed horsepower. That's what you'd see on the other screen that we were talking about when you watch a dyno sweep on YouTube. This is the screen for, if you can see, measured torque or observed torque and power. If I change screens, We can go over here, and now we can see that we're using the calculation or the equation of J607, because there is different equations for different correction factors. But this is a Society of Automotive Engineers J607 correction factor. And you are at 436 and 469. So that's a little higher. If you remember, we go back, 415 uncorrected, 436 corrected. This is the corrected number without inertia correlation. If we take inertia correlation into effect, which means that it's supposed to, if everything works right, correct it back to a steady state number, then we're looking at 443 horsepower, 444 horsepower. So there's three different graphs, three different numbers for the exact same engine. So as a customer, you need to be educated on what you're looking at so that the engine builder or dyno operator doesn't try to tell you that you have higher numbers than what you actually have. So there's pretty much a lot of the in and outs of dynos and Engineered Victories. Till next time, we'll see you later. I hope this helped. Thanks.